Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. The night settles around you, soft, quiet, unhurried, and the universe opens like a vast and silent thought. You are here to rest, to drift, to wander through ideas without needing to hold on to them, as if each concept were a small ripple in a calm ocean, rising for a moment, and then fading gently back into stillness. Tonight your mind approaches one of the strangest boundaries ever proposed in physics, a place with no walls, no surface, no texture, and yet it reshapes our understanding of reality. The event horizon, a region that is not a thing, but a limit, an invisible threshold where the familiar rules of the universe begin to bend, stretch, and sometimes break. You do not need to grasp every detail. You do not need to follow every thread. Tonight is not for solving. It is simply for resting in curiosity, guided by calm, steady science, science made slow and gentle, like a lullaby woven from the language of spacetime. As you breathe, imagine the universe breathing with you, a quiet expansion, a quiet release, as if the cosmos itself were settling down for the night. The event horizon sits in that silence, not like a cliff or a barrier, but like a shift in perspective, a boundary drawn not in matter but in possibility. Far from here, at the edge of a black hole, gravity grows so intense, so overwhelming, that even light reaches its limit. Not abruptly, not like hitting a wall, but gradually, smoothly, as the geometry of spacetime curves more sharply, until every possible path forward bends inward. And the listener, you, are simply allowed to drift near that idea, without tension, without force, without urgency. There is something calming in the notion that even the fastest signals in the universe sometimes reach a point where they can go no farther, not through failure, but through the structure of reality itself. The edge of a black hole is quiet, perfectly quiet. No sound escapes, no light escapes, nothing crosses outward again. And yet if you were falling toward it, you would feel nothing special at all. No sudden pull, no jolt, no change in sensation, just the same silent drift, the same free-fall motion, the same gentle surrender to gravity that planets, stars, and galaxies experience every moment. The event horizon is a boundary that exists not for the falling observer, but for the outside universe watching from afar. A boundary where signals fade, where time stretches, where the laws that describe reality begin to clash. At this threshold, physics does not stop working, but our ability to describe physics does. Equations lose their agreement. Models contradict one another. Classical gravity says one thing, quantum theory insists on another, and the horizon becomes the place where these two languages meet and speak past each other. In this calm space tonight, you are simply allowed to rest within that contradiction, to float gently among ideas that scientists wrestle with in the daylight, while you explore them softly in the quiet of night. There is a strange reassurance in this. Even the universe itself contains unanswered questions. Even nature has regions where certainty dissolves. And that dissolution, that quiet unknowing, is part of the beauty. The event horizon marks a place where predictability fades, where the future inside the boundary is sealed from the outside world, where information follows paths that never return. To think about it is to sit at the edge of understanding, feeling the gentle pressure of curiosity, and allowing yourself to drift beyond it, not with fear, but with peace. Imagine standing at a shoreline. The water does not suddenly end, it simply becomes deeper, darker, quieter, until the bottom disappears from view. The horizon of a black hole is similar. It feels like the point where visibility ends, where light no longer carries the story forward, and where the universe keeps its secrets. As you breathe, imagine each inhale drawing in clarity, and each exhale releasing the weight of needing to understand. The physics will be here, calm, steady, patient, and you can drift along it at your own pace. The idea of the event horizon is rooted in general relativity, a theory where gravity is not a force, but a curvature, a bending of time and space by mass and energy. Near a black hole, this curvature becomes so extreme that all paths point inward, all futures converge toward the center, and the horizon marks the last place where escape is even theoretically possible. Not because something blocks the way, but because every possible trajectory leads deeper in. It is a mathematical surface defined by what cannot return, not a physical layer that something can touch. This is why the edge of a black hole is so strange. It exists and does not exist. It is real and yet intangible. It shapes the universe, but offers nothing to grasp. It is a place where physics behaves differently depending on where you stand. A distant observer sees objects slow, fade, redden, stretch into stillness, never fully crossing. But the falling observer experiences a smooth descent, a seamless continuation of motion, with no sign of the threshold. Two descriptions, two perspectives, both valid, neither wrong, and yet impossible to reconcile completely. This is part of the gentle mystery tonight. The universe allows multiple truths about the same event, depending on where you observe it from, and this multiplicity, this quiet coexistence of viewpoints, forms the essence of the event horizon. A boundary in knowledge, a boundary in communication, a boundary in the structure of space-time itself. You are not asked to solve this paradox. You are only asked to rest beside it, to float at the edge of an idea that challenges even the most advanced theories. There is deep calm here, because complexity loses its sharpness in the slow rhythm of thought. Difficult physics becomes soft, abstract, like distant starlight filtered through a cloud. You can let the details pass by like gentle waves, each one rising, each one falling, each one leaving the surface smoother than before. The event horizon is often described as the place where physics breaks down, but in truth, it is the place where our descriptions break down. Nature continues, the mathematics continues, reality continues. But our frameworks, the ones we use to explain the world, do not fit together. Like puzzle pieces carved by different artists, they touch, but do not interlock. And in that quiet mismatch, there is a kind of wonder. It reminds us that the universe is larger than our understanding, and that this gap is not a flaw, but an invitation to explore, to imagine, to ask questions without needing immediate answers, to rest at the frontier of knowledge and feel no pressure to go further. Tonight, as you drift here, your mind can soften around these mysteries. Everything is allowed to be unfinished. Everything is allowed to be open. Everything is allowed to be quiet. You are simply floating near a threshold where light itself hesitates, a place where time behaves strangely, a place where gravity draws all futures inward, a place where human understanding becomes gentle, humble, curious. This is the edge you are resting beside, the boundary where physics begins to whisper instead of speak, where the universe becomes not a solved equation, but a calm and infinite question. Let yourself settle into that question. Let your thoughts slow. Let your breathing soften. Nothing is required of you. You are only asked to drift, to listen, to rest in the vastness. The event horizon waits quietly in the dark, not demanding attention, not imposing meaning, simply existing as one of the universe's most elegant mysteries. And as you lie here, you become part of that calm, a quiet observer at the limit of what can be known, ready to explore, slowly and gently, the place where physics breaks down and wonder begins. The idea of an event horizon begins with a single word, a quiet word, a word so ordinary in daily life that it hardly demands attention, and yet in general relativity it becomes the foundation of a cosmic boundary. The word is event. In physics, an event is simply something that happens at a specific place and time, a point in space-time, a position, and a moment. Nothing more elaborate than that, just a coordinate, an intersection of where and when. But in general relativity, events are stitched together by the geometry of space-time, woven into the structure of the universe by gravity. Each event sits within a network of relationships, paths of light, paths of particles, paths of influence, all curving through the fabric of the cosmos. To understand an event horizon, you first imagine all the ways events can influence one another, how one moment can affect the next, how information can flow outward, how signals can travel from one location to another. These paths, called world lines and light cones, form the scaffolding of cause and effect. And then, in the quiet math of a black hole, you watch those paths narrow, twist, bend inward, until they point not outward into the universe, but toward a deeper interior, toward a future that leads only one way. This is where the horizon begins to take shape, not as a surface you could touch, not as a membrane you could tear, but as a boundary drawn by these paths, a boundary between the events that can reach the outside world and the events that cannot. The horizon is defined by light itself, by the outermost path where a photon could still escape if it tried, the final moment where outward travel is possible, measured in pure geometry, not in material structure. This is part of what makes an event horizon so strange. Everything about it is mathematical, a set of conditions, a region defined by equations rather than atoms. It does not behave like a wall or a shell or a rigid edge. It is simply the place where all roads leading outward disappear. To stand conceptually near this boundary, you imagine the way light moves in curved spacetime. Near most objects, stars, planets, galaxies, light still finds paths that lead away. Gravity bends its route, but does not forbid escape. But near a black hole, the bending becomes more extreme, more sharp, more irresistible, until the outward paths collapse into a single, fragile boundary. And once inside, every possible path leads toward the center. This is why physicists describe the horizon as a point of no return, but even that phrase can be misleading. It suggests a moment you could mark with a signpost, a threshold with a sudden transition. The reality is gentler, smoother, more subtle. If you were falling freely, simply drifting inward with no engines or thrusters, you would feel nothing special when you crossed the horizon. No increase in pressure, no tearing, no sudden shift. Your experience would be continuous, calm, unchanged. Because the horizon is not a place where local physics changes. It is a place where global information flow changes, a place where the rest of the universe loses access to your future. A boundary of communication, not of sensation. General relativity describes this elegantly, in a way that feels almost dreamlike. The horizon is formed not by matter, but by the shape of spacetime itself. The mass of the black hole curves the geometry so deeply, so profoundly, that the light cones, the shapes that show where signals can travel, tilt inward and keep tilting until they point entirely inside. Every moment beyond the horizon, every event that happens within is sealed from the outside universe, not by force, but by geometry. This distinction is quiet but important. It shifts the idea of a black hole from something violent to something geometric, something defined by curvature rather than destruction. The horizon is gentle, silent, unseen, and yet its consequences are profound. From far away, from the point of view of someone watching an object fall in, the story becomes even stranger. Light leaving the falling object stretches, reddens, weakens. It must struggle against the pull of gravity, climbing uphill through space-time. And as the object nears the horizon, the light it emits becomes so stretched, so faint, so slow to arrive, that it begins to look frozen. The distant observer never actually sees the object cross. Instead, they watch it fade, dim, redden out of visibility. Time itself slows for the falling object, not in its own experience, but in the outside description. This divergence of perspectives is one of the most intriguing aspects of the event horizon. In your own frame, falling freely, nothing unusual happens. You drift inward on a smooth, predictable path. But to someone far away, your time dilates, your motion slows, your signals stretch into silence. You appear to hover forever at the edge, never quite passing through. Two descriptions, two realities, both mathematically correct, both grounded in the same physics, yet completely incompatible in terms of what they see. This is part of the beauty of general relativity, its willingness to allow truth to depend on reference frame, its quiet acceptance that reality can differ depending on where you stand. And at the horizon, these differences reach their peak. The distant observer experiences an infinite slowdown, while the falling observer experiences continuity, a boundary that is absolute in one description and non-existent in another. One of the most calming ways to hold this contradiction is to imagine the horizon as a gently sloping hill. From far away, you are trying to watch someone walk up the hill, but your telescope distorts the view so severely that the person appears to slow down the closer they get to the top. They become smaller, dim, their signals stretched until they vanish, even though the person themselves continues walking at a steady pace. The distortion lies not in the person, but in the geometry through which you observe them. The event horizon works the same way. It distorts the outward image of falling objects, while leaving their local physics unchanged. The meaning of the horizon becomes clearer when you think about escape velocity. Far from a black hole, the escape velocity is small. Near the surface of a neutron star, it becomes large. But at the horizon, the escape velocity reaches the speed of light. Not because something blocks escape, but because spacetime curvature makes outward paths impossible unless you move faster than light, which no object or signal can do. This is not a physical barrier, it is a geometric limit. A limit woven into spacetime itself. From this perspective, the horizon is less like a door and more like the edge of a map, the place beyond which trajectories cannot be drawn outward. A curve in the cosmic fabric that seals off a region not by force, but by the way paths converge. To feel the meaning of the horizon more deeply, imagine releasing a photon outward from your hand as you fall inward. If you are outside the horizon, the photon can still escape, though it fights against gravity. If you are exactly at the horizon, the photon hovers, its outward progress balanced perfectly by spacetime's inward pull. And if you are inside, even the photon cannot escape, because every direction it travels leads deeper in. This is why physicists say that inside the horizon, the radial direction, the direction pointing outward, behaves like time. It is not simply a direction you can choose. It becomes a destiny, a future. Something you move through not by choice, but by the structure of spacetime itself. All of this arises from the mathematics of general relativity, a theory that describes gravity not as a force, but as curvature. The horizon forms where that curvature becomes so extreme, so deep, that the outward-pointing light cones fold inward, a smooth, silent, purely geometric transformation. The most remarkable thing is that none of this requires matter to be present at the horizon. There is no shell, no structure, no ring, no particle distribution. The mass lies deeper inside, in a region hidden from view. The horizon is simply the point where geometry itself changes the possible futures of everything inside it. This shift, from thinking of the horizon as a thing, to understanding it as a boundary of possible events, brings you closer to the heart of what a black hole truly is. It is not the horizon that crushes matter, but the interior curvature. The horizon is only the limit from which nothing returns, a mathematical feature, yet with real physical consequences. Signals sent from near the horizon stretch into longer and longer wavelengths, fainter, slower, until they drift into invisibility. This process is called gravitational redshift, a slow fading, a stretching of light into softer and softer tones until it disappears entirely. At the horizon, this redshift becomes infinite, meaning that no signal from that exact point can ever reach an outside observer. It is not blocked, it is simply stretched beyond all detection, its information carried into a realm where no external measurement can recover it. This is where the horizon becomes more than a geometric boundary. It becomes a limit of knowledge. A place beyond which predictions lose meaning, a region where the outside universe cannot learn what happens next. A quiet boundary between what can be known and what remains hidden. Standing at this conceptual threshold, you feel the strangeness of a universe where information flow defines reality, where light sets the rules, where geometry draws invisible lines that even the strongest signals cannot cross. The event horizon is subtle, delicate, silent. It does not announce itself, it does not resist, it simply exists where the equations say it must. A boundary written into the architecture of spacetime, and in its presence, the universe becomes both clearer and more mysterious. Clear, because the mathematics is unambiguous. Mysterious, because the consequences stretch beyond what our intuition can easily hold. You are drifting near that mystery now, resting at the edge of a region defined not by substance, but by the very shape of reality. And as you float here, the horizon becomes less a place of fear and more a place of quiet wonder. A calm, dark, mathematical shoreline where physics begins to whisper and the unknown begins to take shape. The more closely you look at the event horizon, the more its nature dissolves into pure geometry, a boundary not of matter, but of possibility. It is not something that exists in the same way a surface or object exists. Nothing sits there, nothing accumulates. nothing forms a shell. Instead, the horizon is woven into the shape of spacetime itself, a quiet line drawn by the equations of general relativity, a place where the structure of the universe redirects every future inward. To understand this with a calm and steady mind, imagine taking a particle and placing it near the edge of a black hole. Not inside, not falling, just resting within the gravitational field. You then imagine the possible directions that particle could move, the possible futures available to it. Outside the horizon, some of those futures lead outward, toward distant stars, toward open space, toward the rest of the universe. Some futures point inward, toward the black hole's center, and the particle may choose any of them if it has enough energy. But as you bring the particle closer, gravity narrows its choices. More futures tilt inward, more pathways lead down the gravitational well. The geometry constrains movement not through force, but through the way space-time curves around the mass. At the horizon, every possible future points inward. Every direction, every angle, every trajectory, every motion that could be taken, all of them lead deeper in. Even the path of a photon, which always moves at the speed of light, no longer leads outward. Not because the photon fails, but because space-time no longer offers an outward direction. This is the key. The horizon is where outward ceases to exist. For light, direction is destiny. A photon is not choosing a path, it is tracing the geometry around it. And when that geometry curves so steeply inward that no outward paths remain, the photon must follow. Not by force, but by necessity. This is why the event horizon is not an object. It is a geometric boundary created by the shape of the light cones, those diagrams that show where signals can travel. Outside the horizon, the cones tilt inward but still offer escape routes. At the horizon, they tilt completely, so that even the boundary of the cone points inward. Inside, every direction lies within the inward tilt. And so the horizon appears where the tilt reaches this exact limit, the point of transition between outward possibility and inward inevitability. Even though this boundary is defined mathematically, its consequences are undeniably physical. Once inside, no signal can reach the outside universe. The communication lines are cut, not by a barrier, but by the nature of space-time. When physicists talk about the horizon as a point of no return, they do not mean that something blocks the way. They mean that physics offers no outward future from that point onward. Every timeline leads to the same destination. This subtle distinction is where many misconceptions fall away. There is no wall, no force that drags you back, no membrane wrapping the black hole. If you fall freely, you glide past the horizon without noticing, because nothing locally changes. The curvature is smooth, the gradient is gentle, the equations unfold naturally as you move inward. From your perspective, the descent continues uninterrupted. The apparent violence of a black hole is not felt at the horizon. It lies deeper inside, where the curvature becomes extreme, where tidal forces stretch and compress matter, where the smooth geometry near the horizon steepens toward the singularity. But those inner regions are separate from the horizon itself. The horizon is quiet, elegant, mathematical. To see it from a distant vantage point, to stand conceptually at infinity and look inward, is to witness something completely different, not because the horizon behaves differently, but because your perspective is filtered through the curvature between you and it. This is where proper time and observed time begin to diverge. Proper time is the time experienced locally, the time measured by a clock or heartbeat or falling object. Observed time is what a distant observer sees, a viewpoint influenced by gravitational time dilation and redshift. These two forms of time remain consistent within their own frames, but they differ dramatically near the horizon. Imagine a clock tied to the falling object. As the object drifts inward, the clock ticks steadily, one moment following another, with no sign that something unusual approaches. This is proper time. The falling observer experiences it normally, smoothly, consistently. Now imagine a distant observer watching that clock through a telescope. The signals from the clock must climb out of the gravitational well, stretching as they go. The higher the object, the less stretching occurs. The closer it gets to the horizon, the more the signals weaken, the more the wavelengths lengthen, the more the timing appears distorted. Eventually, as the object reaches the horizon, the signals fade into near-infinite redshift. To the outside observer, the clock appears to slow, then nearly freeze. Its ticks separated by longer and longer intervals until they merge into silence. This is not because the clock stops, it is because the signals cannot overcome the geometry. They lose the battle against curvature. Their information becomes stretched beyond detection. This fading, slow, soft, inevitable, is what makes the horizon feel like an edge. But to the falling observer, no such edge exists. The clock ticks on. Time continues. The horizon passes without a whisper. This duality is one of the deepest conceptual features of the event horizon. It reminds us that physics is not only about what exists, but about what can be known. It tells us that vantage point matters, that reality is woven from both local experience and global description. When physicists say that the horizon is a limit of knowledge, they mean that no information from inside can reach the outside. The horizon marks the dividing line between what can influence the universe and what cannot. It is a boundary of communication, a one-way gate. From the outside, you can never know what an object does after crossing. Its future is hidden, not because something erases it, but because no signal carries that future outward. Inside, the falling object still experiences its own future, its own proper time, its own unbroken sequence of moments. But those moments are sealed from the outside world. They exist, but do not communicate. This intertwining of existence and knowledge makes the horizon one of the most subtle concepts in modern physics. It pushes our understanding of what it means for something to be real. It forces us to consider how much of the universe depends not on objects, but on the rules that allow information to move. Information flow defines physical boundaries more deeply than matter does. The horizon exemplifies this truth. It is a boundary defined by what cannot be said, by what cannot be told, by what cannot be observed. And yet this quiet boundary has profound effects on the world outside it. The fading of signals is one example. Gravitational redshift, the stretching of light into longer wavelengths, grows stronger and stronger as you near the horizon. A beam of light emitted outward from that region loses energy, not by friction or interference, but by climbing through curved spacetime. A photon is never slowed down, never weakened in its own frame, but its wavelength appears longer to an external observer. Its energy appears lower, its color shifts toward red, and eventually into infrared, then into microwaves, then into radio waves, until it becomes undetectable. This is how signals fade, not abruptly, but gradually, smoothly, with an elegance that reflects the geometry behind the phenomenon. The fading also shows why the horizon is not a wall. If it were a physical barrier, the signal would stop suddenly. But because it is a geometric boundary, the signal decays gently, approaching zero only at the horizon itself. This smooth decay is one of the most characteristic features of a black hole. It hints at the delicate balance between gravity and light, between curvature and signal, between what can be known and what becomes forever hidden. The idea that the horizon is not a physical surface becomes even clearer when you consider how it changes. If the black hole grows in mass by accreting matter or merging with another black hole, the horizon expands, not by stretching an object, but by updating the geometry. A larger mass creates a deeper curvature, and the boundary moves outward accordingly. If the black hole loses mass, slowly, very slowly, through Hawking radiation, the horizon shrinks, not by collapsing a surface, but by redrawing the region where escape becomes impossible. The horizon is fluid, dynamic, responsive, a shifting boundary that repositions itself as the underlying mass changes. This behavior confirms that the horizon is not built from material. It is built from the shape of spacetime, a variable geometry, not a static object. To appreciate this deeply, imagine a whirlpool forming in a river. The water does not create a physical barrier, but the flow lines, the trajectories of anything drifting in the current, are pulled inward. At a certain distance, the flow becomes strong enough that nothing floating can escape the inward pull. That distance is not a wall. It is the point where the paths of movement tilt inward. The horizon is similar, except the geometry is four-dimensional and defined by gravity rather than fluid motion. This analogy reveals another subtle truth. The horizon does not care what crosses it. Any object, any photon, any particle that drifts inward will pass through effortlessly. There is no resistance, no increase in density, no structural change. The physics near the horizon is calm, local, smooth. The falling object feels weightless because it is weightless in free fall. The compression and stretching that people often associate with black holes, the tidal forces, depend not on the horizon, but on the size of the black hole. A supermassive black hole would produce tidal forces at the horizon so small that you might not even notice them. The horizon is not where destruction occurs, it is where visibility ends. This distinction creates a feeling of quietness around the concept, a sense that the horizon is serene, mathematical, inevitable, like a simple equation unfolding toward its conclusion. And as you drift through this idea, the event horizon begins to feel less like a frightening edge and more like a soft threshold in knowledge, a place where understanding fades not because the universe resists, but because geometry guides information inward. It is a boundary you cannot see, but whose effects you can feel through the behavior of light, through the pacing of time, through the fading of signals, through the shape of possible futures. A boundary that reminds you gently that physics is not only about what exists, but about what can be known. A quiet, perfectly silent threshold where the universe begins to whisper. Light behaves differently near a black hole, not because the nature of light changes, but because spacetime itself rearranges the pathways along which light can travel. Every photon moves at the same unchanging speed, yet the geometry surrounding a black hole bends all possible routes, all possible futures, into shapes that defy ordinary intuition. To drift into this idea gently, imagine a single photon released in deep space. It follows a straight path, unbent, unaffected. It moves outward freely, carrying information from one region of the universe to another. Its future is open, unconstrained, a simple extension of the geometry around it. But imagine that same photon released nearer to a black hole. As it travels, space-time curves beneath it, gravity reshapes the landscape, and its path bends. Not because something pushes on the photon, but because the geometry itself guides it. Light always moves in straight lines through space-time. But when space-time is curved, straight lines are no longer straight in the ordinary sense. They become geodesics, the smoothest possible routes in a warped terrain. Near a black hole, those geodesics tip inward. They arc gently, then more strongly, then overwhelmingly, until every possible outward-pointing direction collapses into the same inward route. This is the beginning of the horizon's power over light. Not a force, not a drag, but a reshaping of the space through which light flows. To understand this with a soft clarity, think of space-time as a landscape made of valleys and curves. A photon wants to follow the straightest path through that landscape. Far from any massive object, the terrain is nearly flat. The path seems straight in all directions. But near a black hole, the terrain deepens into a well, a steep gravitational depression. The photon still follows the straightest possible route, but that route now curves inward along the shape of the well. Sometimes the inward curve is gentle, and the photon still escapes. Sometimes it is sharp, and the photon arcs around the black hole in a long sweep, a gravitational lensing effect that can wrap light into rings and arcs. And sometimes the curvature becomes so steep that no outward trajectory exists at all. Every direction, every angle, every possibility leads down into the interior. That is the moment the photon reaches the horizon, a place where outward ceases to exist, a place where light must fall inward not because it slows, but because space itself flows inward faster than light can climb outward. This idea that light cannot escape because of geometry rather than friction is central to understanding the strange calm around the horizon. Nothing grabs the photon. Nothing absorbs it. Space-time simply offers no route of escape. To illustrate this gently, imagine a fish swimming upstream in a river. The fish moves quickly, but the current becomes stronger and stronger as it nears a waterfall. At some point, the current flows faster than the fish can swim. No matter how strongly it moves, it drifts downstream. The fish does not fail, the current simply outpaces it. Now imagine the fish is made of light, always moving at the same speed, always swimming as fast as nature allows. The river is space-time. The current is the curvature flowing inward. At the horizon, the inward flow of space-time matches the speed of light. No matter how hard the photon tries to swim outward, it is carried inward, not by force, but by the current of space-time. This is the heart of why light cannot escape once it is inside the horizon. The structure of the universe at that location no longer offers a path leading outward. Every possible future points inward. This is why physicists describe the horizon as a null surface. A surface made not of matter, but of light-like paths, the very last set of outgoing routes that still cling to the edge of escape. Walk along this surface, and you would find that every step forward is still hovering at the brink between escape and fall. It is a delicate balance between outward and inward futures, a limit where light neither rises nor escapes, but drifts sideways along the boundary. To see this even more clearly, imagine a photon emitted exactly at the horizon. If it points inward, it falls. If it points sideways, it remains forever on the horizon, moving around it without leaving. If it points outward, that outward direction no longer exists. The geometry has closed it off. This creates a profound, gentle insight. The horizon is not a location where light stops. It is a location where light's outward possibilities vanish. The geometry becomes absolute. The behavior of photons reveals the structure of spacetime in its most extreme, elegant form. This is why physicists often treat photons as tracers, tiny probes that reveal the shape of spacetime. Their paths show how the universe curves. Their trajectories outline the invisible structure around the black hole. Light becomes a map maker, a silent cartographer of geometry. Near the horizon, that map grows increasingly strange. Photons emitted outward become weaker. Their energy drains, not through loss but through redshift. A photon climbing out of a deep gravitational well must stretch its wavelength, giving up energy to escape. Far from the black hole, this stretching is small. Near the event horizon, the stretching grows enormous. A visible photon becomes infrared, then microwave, then radio, then so long and gentle that its oscillations take seconds, minutes, hours. Eventually, they stretch toward infinity. This is what physicists call gravitational redshift. The deeper the photon begins, the more of its energy is consumed by the climb. At the horizon, the climb becomes infinite. Any photon emitted outward becomes infinitely stretched, so its energy becomes infinitely diluted. It fades into nothingness when seen from outside. To the photon, nothing unusual happens. It still oscillates, it still carries information, but the observer far away never receives it. The light becomes too faint, too stretched, too slow to arrive. The horizon swallows not the photon, but the possibility of its detection. This is why scientists say that the horizon is the place where light becomes silent. Even the fastest messengers of the universe, the carriers of information, the tracers of reality, lose their ability to report what happens inside. Not because the photons cease to exist, but because the universe stops allowing their stories to be heard. The horizon creates a perfect quietness, a calm that cannot be broken, a silence enforced not by force, but by geometry. In this silence, the horizon becomes the dividing line between what can be known and what remains forever unspoken. It is the place where physics, in its classical form, meets its limits. But the behavior of light near the horizon reveals something even deeper, something that touches on the essence of causality itself. Because light is the ultimate speed of information, anything that cannot outrun the inward curvature is trapped. Anything that cannot send signals outward loses contact with the external universe. And once signals cannot escape, the region becomes causally sealed. The horizon is thus the boundary of causality. The outer universe cannot influence what happens inside, and the inside cannot influence the outside. A perfect separation, a quiet partition in reality. This partition grows as more matter falls in. It shifts and breathes with the mass of the black hole. It is flexible, responsive, alive in its own geometric way. It expands when light fails to escape, and it contracts only over immense timescales as black holes slowly lose mass through quantum radiation. Light marks the boundary. Light reveals its shape. Light is what makes the horizon visible in theory and invisible in practice. And perhaps the most beautiful truth is this: the horizon is not a surface where light crashes. It is a surface where light's story ends for the outside universe, where the last chapter of outward communication is written, and where the rest of the book unfolds in darkness. As you drift with this idea, you feel the calmness behind it. A serenity born from geometry, a silence woven into the structure of spacetime. The universe does not shout at the horizon, it whispers and then becomes still. This stillness is the essence of light at the edge, a quiet threshold where photons trace the last possible paths outward, a place where geometry shapes destiny, a place where even the fastest signals yield to the curvature of spacetime, and in that yielding, the cosmos becomes wonderfully, profoundly calm. Light near the event horizon behaves like a messenger walking along a narrowing ledge, a ledge that becomes thinner and steeper the closer it comes to the boundary where escape ends. The geometry constrains it quietly, softly, slowly, removing every outward path until only inward futures remain. This soft confinement is not violent. It is not abrupt. It happens the way twilight deepens, smoothly, imperceptibly at first, until suddenly the last rays fade into night. To see this more clearly, imagine light traveling through curved spacetime as though it were tracing the surface of a sphere. On a flat plane, you can choose any direction freely, but on a curved surface, the straightest path still curves, and that curvature influences where the path ultimately leads. Replace the sphere with the gravitational well around a black hole, and the light path begins to bend inward, obeying the geometry it cannot resist. In the region just outside the event horizon, this curvature becomes dramatic. A photon aimed outward at a shallow angle is pulled inward, its trajectory bending until it spirals into the black hole. A photon emitted at just the right angle may orbit the black hole, caught in a delicate, unstable loop known as the photon sphere. This is a ring of null orbits, a place where light neither escapes nor falls immediately, but dances around the black hole in fragile circles. But even this orbit is temporary. Any tiny disturbance, any deviation, any nudging, pushes the photon either outward toward escape or inward toward capture. Light cannot hold balance forever. The curvature is too extreme, too unforgiving. The photon sphere is a razor's edge in spacetime, and photons sliding along it do so for only a transient moment. This transition, from escape to orbit to inevitable fall, reveals something important. Even outside the horizon, light is not always free. It follows paths carved by the gravitational landscape, paths that grow increasingly constrained as one approaches the boundary. The deeper the photon begins, the more energy it must expend to climb outward. This energy loss does not come from friction or interaction, but from the structure of spacetime itself. It's as though the photon must stretch its very identity, its wavelength, to reach distant observers. This stretching becomes more dramatic the closer it starts to the horizon. A photon emitted from just outside the horizon must give up nearly all of its energy to escape. It arrives at the outside universe as a faint, long, weak signal, if it arrives at all. This is why gravitational redshift grows without bound as the emission point approaches the horizon. A photon emitted exactly at the horizon would require infinite energy to escape, which nature does not allow. And so the outward path simply does not exist. It is not that the photon fails, it is that the universe does not grant an outward trajectory. The horizon marks the place where outward becomes undefined. This is the core of why even the fastest possible signal cannot escape once inside. The horizon is not a prison wall, it is the end of outward geometry. And because light defines the causal structure of the universe, because it sets the ultimate speed at which cause can follow effect, the horizon becomes the boundary where causal influence ends. Anything within can no longer influence the outside. Signals decay into silence. Information becomes trapped in futures that cannot reach the external universe. This is why the horizon is often described as the place where light becomes quiet. Not erased, not destroyed, just silent. Imagine sending a pulse of light outward. At first, the pulse climbs slowly, weakening as it goes. Then the climb becomes harder, stretching its wavelength further. And finally, as it approaches the horizon, the pulse is stretched so long that a single oscillation might take longer than the age of the universe. At that point, the signal becomes indistinguishable from nothing at all. For the falling observer, none of this happens. Their light behaves normally. Their clock ticks normally. Their experience remains smooth. Light travels at the same speed. Wavelengths remain unchanged in their local frame. Signals behave as expected. But to the distant observer, the light stretches into silence as though it were fading into a soft, unreachable dusk. This gentle divergence between frames is one of the most intriguing aspects of black holes. One observer sees light vanish into calm invisibility. The other experiences no such fading. Both are correct. Both describe the same physics. Both represent different projections of the same geometry. This coexistence of perspectives becomes clearer when you consider how gravitational redshift works in terms of energy. A photon carries a frequency. Frequency corresponds to energy. So as the photon climbs out of a gravitational well, its frequency drops, its color shifts, its energy drains away. In deep gravitational wells, such as near a neutron star, this shift is measurable. Near black holes, it becomes extreme, overpowering, transforming visible light into whisper-like waves. The horizon is the ultimate limit. A photon emitted outward from that boundary would have to stretch an infinite amount. An infinite redshift means zero received energy. Zero information. Zero detection. This is why light becomes silent at the horizon. The silence is not sudden, it is not abrupt. It is a smooth fade, a transition from the knowable to the unknowable, from the visible to the invisible. The geometry ensures that outward messages dissolve into infinite slowness and infinite softness. It is as though light is still speaking, but its words stretch until each syllable takes forever to form. This fading has another implication. If no outward signal can escape, then the horizon is the boundary of communication. No message sent from within can ever reach the outside, not because messages cease, but because the universe prevents their arrival. This is why the horizon is also called a causal boundary. The inside region is cut off from the external universe. Events inside cannot affect anything outside. Not through motion, not through signals, not through radiation. Causality ends there. A perfect silence beyond which the external world can only imagine what unfolds. And yet, the horizon itself is dynamic. It responds to matter falling inward. It expands when mass enters. It reshapes when space-time changes. This flexibility reminds us that the horizon, though silent, is not inert. It is tied intimately to the flow of light and the curvature that shapes it. This entire structure, the bending of light, the narrowing of trajectories, the soft extinction of outward messages, comes from one profound fact. Light always takes the straightest path through space-time, and near a black hole, that path points inward. This insight dissolves the old idea that gravity pulls on light like a force. Instead, light simply follows geometry, and geometry itself changes near the horizon until every possible straight line leads to the same destination. Even the famous notion of escape velocity becomes secondary. It is not that the escape velocity reaches the speed of light in the traditional sense. It is that no outward path exists for anything to escape into. Escape is not prevented by force. Escape is prevented by the absence of outward futures. To drift deeper into this understanding, consider the concept of null surfaces. A null surface is a region of spacetime where every point lies along a light-like path. The event horizon is precisely such a surface. It is woven from null trajectories, the paths of photons that barely fail to escape. These photons define the boundary. They skim along it, never falling in, never climbing out. Their existence creates the horizon's shape. They form a kind of silent scaffolding of light, marking the transition between regions. This structure means the horizon is made of information paths, not matter, a boundary defined by what light can barely achieve. Inside the horizon, light-like paths tilt inward so sharply that no photon can return. Outside, light-like paths tilt outward enough to allow signals to escape. The horizon is the knife edge between these two regimes, a boundary of geometry, a boundary of information, a boundary of causality. And as you rest with this idea, the horizon becomes something gentle, not a monster, not a devourer, not a violent edge, but a smooth, silent surface where the universe transitions from regions that can speak to regions that can only remain quiet. This is where even the fastest signals in nature reach their limit. This is where light finally surrenders its outward path. This is where geometry becomes destiny, and in that surrender, the universe becomes still, a calm, quiet cosmic silence at the very edge of what can be seen and what can be known. Time behaves strangely near a black hole, not because time itself breaks, but because gravity reshapes the rhythm of moments. The closer one comes to the event horizon, the more time spreads out, stretches, softens into different forms depending on where you observe it from. This difference is not an illusion. It is a structural feature of space-time, built into the geometry by the presence of extreme curvature. To feel this idea gently, imagine two observers drifting in the universe. One remains far away, floating in the calm, nearly flat expanse of weak gravity. The other falls inward, letting go, surrendering to the pull of the black hole. Both carry clocks, both see their clocks tick normally. Both experience their own passing moments as smooth and unbroken. Yet the two clocks disagree. Not because either clock malfunctions, but because the space-time each clock inhabits is shaped differently. Gravity slows time, not metaphorically but literally. The flow of time itself changes with gravitational strength. And near the event horizon, gravity is stronger than anywhere else in nature. Time dilates, moments lengthen. Processes slow when viewed from afar. The falling observer does not notice this. Their heartbeat remains steady, their thoughts remain clear, their breathing follows its natural rhythm. Every internal process continues at the same pace it always has. But the distant observer sees the falling one slow down. Not dramatically at first, just subtly. Signals take longer to arrive, light grows redder, responses grow delayed. As the falling observer approaches the horizon, the delay increases. Signals from their clock become stretched. Each second appears a little longer than the one before. Time dilation deepens into something profound. When the falling observer is extremely close to the horizon, their signals take so long to reach the outside that the distant observer perceives them almost frozen, suspended in a single moment, as though time has stopped. This is one of the most beautiful and quiet distortions of general relativity. Two observers sharing the same universe, yet experiencing completely different flows of time. The falling observer sees nothing unusual. They continue drifting inward. The horizon moves past them in a single ordinary moment. They feel no resistance, no change, no barrier. Crossing the event horizon is smooth, silent, unremarkable. But the distant observer never sees this crossing. To them, the falling observer becomes dimmer, slower, redder, until all signals fade into nothingness. The falling figure seems to dissolve in slow motion, never quite reaching the horizon. Each perspective is correct. Each reflects a different slice of space-time. Neither is privileged over the other. This is the quiet paradox of time near a black hole. To drift deeper into this idea, imagine shining a flashlight while falling inward. The beam travels outward, carrying information about your position. Far away, an observer watches the light, but the climbing photons must fight against the steep curvature. Their wavelengths stretch, their energy drops, their arrival slows. Eventually, as you hover just outside the horizon, the light becomes too long wavelength to detect. Your signals fall into gravitational silence. To the distant observer, you fade away into a final whisper of red light. But in your own frame, nothing fades. Your flashlight behaves normally. The beam shines, the photons propagate, the local experience remains unaffected. Your time flows forward. This difference shows how deeply relativity reshapes intuition. Time is not universal. It is not the same everywhere. It depends on the geometry that surrounds you. Near the event horizon, time diverges into two realities. One appears nearly paused, the other flows normally. Both coexist without contradiction. This is why physicists often speak of two forms of time: the proper time you experience as you fall, and the coordinate time measured by the distant observer. Proper time is local, your own rhythm of moments. Coordinate time is global, a perspective stretched across vast, curved distances. Near the horizon, the difference between these two forms of time becomes enormous. The falling observer might experience a few seconds or minutes of descent. The external universe might see those same moments stretched across years, centuries, even longer. In extreme cases, while you fall inward, the outside universe could age unimaginably. Stars could burn out, galaxies could collide, cosmic structures could evolve tens of millions of years into the future, all in the time it takes you to drift through a handful of calm instants. This is the essence of relativity. Time is not a universal river. It is a landscape of currents, a mosaic of flows. Each region, each observer, each gravitational field shapes time in its own way. Near a black hole, the currents of time diverge most intensely. The falling observer sees the outside universe accelerate. Distant light blue shifts. External processes seem to speed up, compressed into a rapidly unfolding cascade. This is the inverse of the distant observer's experience. What slows your descent for them accelerates their universe for you. The symmetry is beautiful. One perspective slows, the other quickens. Each perspective completes the other, like two complementary halves of a single cosmic truth. The event horizon deepens this division. Once crossed, the falling observer's future becomes sealed from the outside, not because their time ends, but because the outside universe no longer receives information from inside. Their timeline continues inward, smoothly and naturally, while the rest of the cosmos becomes unreachable. And yet, their experience remains ordinary. Their clock ticks, their thoughts continue. Their descent into the interior feels like nothing extraordinary. This quiet continuity is one of the most surprising features of black hole physics. Crossing the horizon is uneventful, unremarkable. A smooth passage through a place where time stretches differently depending on who watches. The distant observer never sees this crossing. They only see the illusion of freezing, a mirage created by the geometry of gravitational time dilation, not by any physical barrier. It is a visual effect of curvature, not a literal suspension. Inside the horizon, time becomes even stranger. The inward direction becomes the direction of the future, a coordinate transformation so profound that it defies normal intuition. You cannot choose to move outward any more than you can choose to move into the past. The geometry of spacetime dictates your future, guiding you deeper inward as inevitably as the next beat of your heart. This transformation is smooth. It happens with no sensation. Your proper time simply continues unfolding. The components of spacetime reorganize themselves around you, changing the meaning of directions without any abrupt change in your experience. This subtlety is essential. General relativity does not allow sudden disruptions at the horizon. The curvature is finite there. The geometry is continuous. Only the global structure of spacetime changes, not the local physics. This is why the falling observer feels nothing at the horizon. No tearing, no stretching, no sudden increase in tidal forces. All dramatic effects lie much deeper inside, where curvature becomes extreme. Time near the horizon holds a quiet duality, a serene coexistence of perspectives that can never fully communicate yet never contradict the laws of physics. The falling observer crosses into a region where the universe behind them accelerates, its timeline unfolding rapidly. The distant observer watches the falling observer freeze into silence, and the horizon becomes the boundary where these two narratives diverge forever. It is a calm divergence, a gentle separation of realities, not chaotic, not violent, but soft, like two rivers that flow side by side but never meet again. As you rest with this idea, you begin to see that the event horizon is not simply a place where escape ends. It is a place where time itself becomes layered, a place where the universe allows different truths to exist simultaneously, a place where perspective shapes reality in a profound way. And in this layered structure, the horizon becomes not only a boundary in space, but a boundary in time, a quiet threshold where the meaning of before and after changes depending on who watches, a place where physics becomes both precise and dreamlike. A region of the universe where time drifts, stretches, and softens into forms that invite wonder, curiosity, and gentle reflection. Time near a black hole becomes a region of quiet disagreement, a place where two observers can look at the same physical process and describe it in completely different ways, not because either is mistaken, but because the geometry allows both truths to exist simultaneously. This duality is not a breakdown of physics. It is the natural consequence of how space-time bends under extreme gravity. To settle into this idea, imagine that you are falling inward, calm, weightless, unafraid, simply drifting along the natural trajectory of free fall. Your experience of time remains smooth. Nothing changes about your own rhythm of existence. Your thoughts unfold with their usual cadence. Your motions feel familiar. Your heartbeat stays steady. Now imagine a distant observer watching you. They measure your descent using their own coordinate time, time diluted only gently by weak gravitational fields. They watch you approach the event horizon, but they see your motion slow. They see the light from your body stretch. They see the timing of your signals unravel into longer and longer intervals. What they see is not your experience. Their time is not your time. The equations of general relativity allow both narratives. Your proper time, your internally experienced time, traces a perfectly normal fall. The distant observer's time, their global coordinate time, traces a slow approach that never completes. This split is not an illusion, it is built into the space-time geometry itself. Two observers following different world lines inhabit different slices of the universe's temporal fabric, and nowhere is this difference more dramatic than at the event horizon. In your proper time, crossing the horizon happens as a simple, ordinary moment. There is no sensation of a boundary, no flash, no distortion, no resistance. The curvature at the horizon is finite. The geometry is smooth. You pass through as though drifting across an invisible line drawn in water. But in the distant observer's time, you never cross. Your image fades, your signals stretch, your motion slows into near frozen stillness. You become a dim ember suspended at the edge of the horizon, caught in an eternal moment where progress appears impossible. This divergence is one of the most important insights in black hole physics. The event horizon is not where strange physics happens to the falling observer. It is where strange physics happens to the relationship between the falling observer and the outside universe. It is the place where communication breaks down, where signals lose their ability to climb outward, where the shared timeline of two observers splits into two incompatible descriptions. And inside this split, time itself becomes layered, like two melodies played simultaneously, each following its own rhythm, each true within its own frame. For the distant observer, your time dilates. Their clock ticks while yours appears to slow. For you, your time feels normal while their universe accelerates around you. This inverse perception reveals the gentle symmetry in relativity. If gravity slows time for you relative to them, then their time must speed up relative to you. Imagine watching the cosmos behind you as you fall. Galaxies shift, color changes, light compresses into blue-shifted tones. Processes that once took millions of years begin to unfold more quickly. Stars age, structures evolve. The universe's distant regions accelerate through history as your descent continues. Not because you're moving fast in your own frame, but because the curvature between you and the outside distorts the timing of their signals. This is another key idea. Time dilation is not something you feel. It is something measured between observers. It is a comparison, not an internal experience. Gravity changes the pace of time depending on location. Close to the horizon, the difference grows enormous. This leads to another quiet realization. If you fall into a black hole, you can watch the external universe's future unfold, not in perfect detail, but in accelerated form. Light from distant galaxies reaches you in a compressed timeline. Events from the far universe race ahead. The cosmos ages around you, and yet you feel nothing unusual. Your body does not speed up. Your thoughts do not rush. You simply witness a different slice of the universe's evolution because you occupy a region where time flows more slowly relative to the cosmic average. It is not your time that changes. It is the outside time that appears to accelerate. This perspective shows how deeply gravity influences what the word now means. In everyday life, we assume that now is universal, a moment shared by all observers. But near a black hole, the meaning of now dissolves. Simultaneity becomes ambiguous. Different observers inhabit different slices of the temporal structure. Their notion of the present diverges. The horizon sharpens this divergence. It is the point at which the distant observer's now can never include events from inside. Their present and your future no longer connect. Their timeline separates from yours forever. This separation is smooth, quiet. No signal announces the moment. No marker indicates the transition. It is simply the result of light's inability to travel outward. And because light defines causal order, because causality follows the paths of photons, the horizon becomes the place where causal structure fractures. You feel no fracture. You feel no break. Your proper time continues. But the outside universe no longer receives your moments. Your future becomes something the external world can never witness. This gentle vanishing of causal connection is one of the most fascinating aspects of the horizon. It does not sever your timeline. It simply encloses it. It creates a region of space-time whose future cannot influence the outside. From inside, you still exist. You still experience moments. You still follow your world line. But your world line is now sealed off behind a boundary drawn by the geometry of space-time. This idea becomes even more subtle when you consider the meaning of before and after. Inside the horizon, moving inward is not a choice. It is a future. The inward direction becomes time-like. It is something you move through simply by existing. You do not feel pulled, you do not feel compressed. You simply follow the natural unfolding of events as dictated by the geometry around you. This transformation, the reassigning of direction to future, is one of the quiet wonders of general relativity. Only a black hole can reshape spacetime so deeply that directions themselves acquire new meanings. And yet, nothing in your local physics alerts you to this change. Your proper time remains your guide. Your experience remains smooth. The horizon does not create turbulence. It does not tear or distort. It is simply the place where one geometry transitions into another. The distant observer, however, sees none of this. Their reality ends at the horizon. For them, your final visible moment lasts forever. This is why black holes appear as perfect absorbers. Objects never seem to vanish inside. They only fade and fade and fade into the soft silence of redshifted light. The deeper truth is that disappearance does happen, just not in the distant observer's coordinate time. It happens in your proper time, quietly, smoothly, in an ordinary moment. This duality of descent, the smooth fall and the frozen appearance, creates a profound divide in how time is perceived near the horizon. It shows that time is not a global river. It is a local flow. It is shaped by gravity. It is bent by curvature. It changes depending on where you stand and how you move. The horizon is the place where these differences sharpen into two fully incompatible descriptions that coexist peacefully. A place where the meaning of time ceases to be universal. A place where relativity reveals its deepest nature. And as you rest with these ideas, you begin to feel the quiet strangeness of a universe in which time itself is flexible, malleable, woven from geometry. Near the event horizon, time becomes a soft, layered structure, a calm landscape where different observers experience the same physical reality in beautifully different ways. And this layered structure, this gentle divergence of moments, is one of the reasons the event horizon remains one of the most captivating mysteries in all of physics. There is a quiet strangeness near a black hole, a place where two descriptions of reality can exist side by side, each complete within itself, yet impossible to merge into a single picture. It is a region where nature allows multiple truths to be simultaneously valid, where perspective is not merely a matter of viewpoint, but a matter of physics. To approach this idea gently, imagine that you and a distant observer are both watching the same event unfold. You fall inward toward the black hole. They remain far away, floating in a calm region of almost flat space-time. You share a history. You share a beginning. You share a universe governed by the same physical laws. Yet as you draw near the horizon, your realities begin to diverge. The distant observer sees your motions slow. Your lights stretch into redness. Your signals fall behind until you appear nearly suspended at the edge, hovering in a slow twilight that seems to last forever. But inside your own frame, nothing slows, nothing freezes, nothing stretches into timelessness. Your fall continues with gentle inevitability, smooth, unobstructed, normal. The horizon passes beneath you as though it were no more than a coordinate on a map, a place you drift through with no sensation of crossing. This creates two incompatible pictures of reality. In one, you never reach the horizon. In the other, you cross it effortlessly. And yet both descriptions are correct. This is one of the profound insights of modern physics, that reality is not a single narrative, but a set of overlapping descriptions, each tied to the world line of an observer. General relativity teaches that motion alters perception, gravity alters time, and perspective itself becomes part of the structure of spacetime. A black hole magnifies these differences until they can no longer be reconciled into a single shared view. The horizon becomes the boundary between descriptions. To the distant observer, the horizon is an infinite gravitational well, a place where time slows into stillness. To the falling observer, the horizon is empty space, a region with no physical edge, no wall, no obstruction. Two realities, both genuine, both derived from the same laws. The difference lies not in physics itself, but in which slice of spacetime each observer inhabits. This is where the idea of complementarity enters. The notion that two seemingly contradictory descriptions can both be true as long as no observer can access both simultaneously. In the case of a black hole, no one remains outside and inside at the same time. No one can compare the two accounts from a single vantage point. No contradiction can be revealed because no single observer can test both perspectives. The horizon protects the consistency of nature by separating these viewpoints through causality itself. Those outside can never receive signals from inside. Those inside can never send information back out. The two narratives are divided by the geometry of space-time. This means that physics never actually breaks down at the horizon. It is the explanation that becomes fragmented. The ability to tell a single unified story slowly dissolves, not because reality fractures, but because observers become permanently separated by the flow of space-time. To the distant observer, your frozen image remains suspended near the edge, fading into the long wavelengths of redshifted light. They watch your last visible moment stretched across an eternity, as though you were caught between motion and stillness. To you, they drift into the past. Your signals from the outside world become compressed. Their universe accelerates, their timeline races ahead, and then the horizon slips past you without drama, without force, without any change in local physics. This leads to a deeper truth. Space-time is not a stage on which events unfold. It is a participant. It shapes motion, it shapes causality, it shapes the perceptions and experiences of those who travel through it. The horizon is where this shaping becomes absolute. Inside the horizon, the inward direction becomes the future. It is no longer a place you move toward. It is a place you are drawn into because your world line is tilted inward by the geometry. You cannot choose to move outward any more than you can choose to move into yesterday. The horizon rearranges the meaning of direction. Yet nothing about this geometric transformation is revealed to your senses. Locally, your environment seems smooth. Your body feels light. There is no violent stretching at this boundary, no tearing apart of atoms, no immediacy of destruction. The drama lies not in local forces, but in the global shape of space-time, a shape you cannot perceive in a single moment. This illustrates a subtle but important fact. General relativity is not about forces acting on objects. It is about the curvature of space-time guiding their motion. And at the horizon, this curvature becomes so profound that two observers can no longer agree on the sequence or meaning of events. One observer sees a boundary that nothing crosses. Another sees no boundary at all. Each lives within a different rendering of the same universe. Each description is valid, but only within its own domain. This division becomes even more interesting when you consider that neither observer's description leads to inconsistencies in physical prediction. The distant observer can predict what they will never see from the inside. The falling observer can predict what they will experience regardless of the outside view. The mathematics supports both accounts. Reality becomes a tapestry woven from multiple overlapping narratives. No single thread captures the entire picture. The event horizon is where these threads diverge into incompatible, yet coexisting truths. And this leads to the gentle realization that physics does not break down at the horizon. What breaks down is the idea that a single global viewpoint can describe the entire universe. The horizon is the boundary where global description becomes impossible. Inside, your story continues. Outside, your story ends at the last visible moment. Both are complete narratives. Both reflect the geometry of space-time, but they cannot be merged. This is not a flaw, it is a feature of relativity. The horizon protects consistency by separating the regions in which each narrative applies. To drift deeper into this idea, imagine space-time as a vast landscape. Observers travel through it along paths shaped by gravity. Each observer's path determines what portions of the landscape they can see. Some valleys are hidden from others. Some ridges divide one region from another. The horizon is one such ridge, not because it is tall or sharp, but because it marks where paths diverge forever. Once you descend into the valley past the ridge, you can no longer send messages back. Your perspective becomes isolated, self-contained. The world behind the ridge continues, but its horizon now conceals you. And from above the ridge, your descent is never witnessed. Your last moment remains visible, fading slowly, stretching endlessly, until it becomes part of the background quiet. This metaphor captures the essence of complementarity, the idea that the inside and outside views form two different but consistent descriptions of reality. The horizon is where these dual realities separate, a gentle division in the fabric of explanation. a quiet boundary where the universe reveals its layered nature. And as you rest with these thoughts, you begin to feel the strange serenity in this structure. The universe does not contradict itself. It simply offers different truths to different observers. The event horizon becomes not a place of violence, but a place of symmetry, a place where reality folds into two intertwined perspectives, neither wrong, neither incomplete, simply different. A place where nature is consistent even when our descriptions diverge. A place where physics remains whole, but explanation becomes softly fragmented, like two reflections of the same star shimmering across a curved surface of water. The boundary between inside and outside becomes even more intriguing when you consider that neither observer, the one far away nor the one falling inward, ever violates the laws of physics in their own frame. Both experiences obey general relativity with perfect consistency. Both are rooted in the same geometry. Yet their conclusions about reality differ so dramatically that it seems at first glance as though physics itself must break. But it doesn't break. It simply reveals that observers define what reality means within the region of spacetime they can access. The distant observer lives in a universe where nothing crosses the horizon. Their instruments never register an object entering the black hole. Their clocks never show a moment after which the falling observer is inside. Their equations describe an event horizon as the ultimate boundary, a limit never breached, never crossed, never touched by anything in finite coordinate time. This is the outside reality. The falling observer experiences a completely different universe. They drift inward freely, their time unfolding smoothly, their world line carrying them beyond the horizon as though it were simply another location in space. They see no freezing, no infinite delay, no barrier. Their horizon crossing is not a cosmic event. It is a mundane moment, a continuation of their descent. This is the inside reality. And the extraordinary truth is that both are correct. The horizon becomes a kind of interpretive boundary, not a physical obstruction, but an epistemic one, a boundary in knowledge, a boundary in what each observer can consistently describe. For the distant observer, the falling one never vanishes into the black hole. They only fade to red, dim, stretch, and eventually disappear into wavelengths too long to detect. The horizon becomes a veil through which no information returns. For the falling observer, the distant universe rushes ahead into the future, unfolding at an accelerating pace. Stars age more quickly, galaxies drift, cosmic structures evolve, and the horizon slips behind them with no more resistance than drifting through a patch of empty space. Two realities, two descriptions, two incompatible viewpoints. And yet the structure of spacetime protects the harmony between them. Neither observer can compare notes after the crossing. Neither can reveal the contradiction to the other. Causality enforces the separation. The distant observer cannot receive signals from inside. The falling observer cannot send them. The two descriptions become sealed islands of truth, each valid within its own domain, each self-consistent. This gentle separation is what physicists call complementarity, a concept borrowed from quantum mechanics but given a new form here. A cosmic duality, where mutually exclusive descriptions are both needed to capture the full behavior of nature. The horizon becomes the boundary where these descriptions diverge and cannot be unified into a single global picture. This is the place where explanation breaks down, even though physics itself remains smooth and complete. To drift even deeper into this idea, imagine the horizon as a sheet of spacetime that folds perspectives differently, depending on which side you occupy. From far away, the sheet appears rigid, a barrier that no world line crosses in finite time. From up close, the sheet is flexible, a region where free fall remains unimpeded. The fold is mathematical, not physical. It lives in the equations, not in the experience. This folding means that the inside and outside observers are not contradicting each other in any operational sense. They simply live in different coordinate systems, different causal structures, different accessible regions of space-time. This is why physicists sometimes say that the event horizon is the place where global time ceases to exist. Not because time stops, but because the notion of a single universal timeline becomes impossible to define. The concept of now inside can never be compared to now outside. The two timelines diverge and never reunite. This divergence is what allows both perspectives to remain true. The horizon protects the consistency of physics by preventing the two viewpoints from interfering. It is a barrier in information, but not in motion, a boundary in knowledge, but not in space. This delicate balance reveals something profound about the nature of truth in physics. Truth depends on the observer. It is not arbitrary, not subjective, but rooted in the structure of spacetime itself. Your world line determines what you can know. Your motion defines what you can experience. Your causal past and future carve out the slice of reality available to you. Near a black hole, these slices diverge dramatically. The outside observer's slice includes every moment of your approach but never sees the completion of your fall. The inside observer's slice includes the horizon crossing, the interior, the path deeper toward the singular region, but never again includes the world behind them. The horizon separates these slices as cleanly as a mirror that reflects two different worlds, depending on which side you stand. And yet both worlds arise from the same geometry, the same equations, the same curvature, the same physical laws. The contradiction is only apparent when you try to view both perspectives simultaneously, something the universe prevents. This leads to another gentle realization. The horizon is not where physics breaks, it is where global descriptions break. It is where our attempt to create a single universal narrative becomes impossible. Nature is not troubled by this. It does not require a single story. It allows many. It allows overlapping, complementary descriptions that cannot be combined but never conflict. This layered reality becomes most striking when you consider energy and temperature at the horizon. To the distant observer, the horizon glows faintly. Quantum physics predicts a temperature, a gentle warmth, not from classical heat but from quantum fluctuations. This is Hawking radiation. To the falling observer, the horizon is cold, silent, featureless, no glow, no heat, no radiation. Two thermal realities, two completely different experiences of the same region. And again, both are correct. The radiation seen from outside is the result of the structure of spacetime as perceived in that frame. The falling observer, moving along a free-fall world line, does not perceive the same quantum excitations. Their frame renders the horizon inert. Reality becomes observer-dependent in a way that is subtle and beautiful. The horizon is not a furnace in the local sense. It is a thermodynamic surface only in the perspective of those who hover outside. It radiates only for observers who remain static in curved spacetime, a viewpoint impossible to maintain at the horizon without infinite acceleration. For the falling observer, there is no such acceleration. Their path is natural, unforced, smooth, and the horizon offers no thermal signature. Two realities, two temperatures, two interpretations of quantum vacuum. This is the ultimate expression of complementarity, the idea that different observers may assign different properties to the same region of spacetime without contradiction. From the outside, the horizon has entropy. From the inside, it has none. From the outside, it radiates. From the inside, it is silent. These dual descriptions are not errors. They are features of a universe where information, causality, and geometry intertwine in ways that challenge classical intuition. And as you let this idea settle gently, you see why physicists say that black holes are not simply objects. They are perspectives. They are geometries that reveal how profoundly reality depends on who is watching and where they stand. Information behaves strangely at the edge of a black hole, not because information disappears in any physical sense, but because the laws that govern it seem to disagree about what is allowed to happen. Classical physics suggests one story. Quantum physics insists on another. And the event horizon becomes the quiet boundary where these two narratives collide. To begin, imagine that every particle, every photon, every ripple of energy that falls into a black hole carries information. Information in physics does not mean knowledge or language. It means the precise physical arrangement of a system, the quantum state that defines what is happening at the microscopic scale. Information is the bookkeeping of the universe. It tracks what is possible. It records what has occurred. It ensures that evolution in physics remains consistent. In classical general relativity, anything that falls through the event horizon is lost to the external universe forever. Its information becomes sealed inside a region from which no signals can escape. Spacetime itself prevents any retrieval. The interior of the black hole becomes a vast archive from which no page can ever be returned. But quantum mechanics does not allow this. Quantum theory demands that information cannot be destroyed. The evolution of a quantum system must be reversible at a fundamental level. Every state must come from a previous state that is uniquely determined. Nothing can simply vanish into oblivion. This leads to a deep tension. The horizon allows objects to fall in and never return signals outward. Classical physics accepts this silence. Quantum physics does not. The universe cannot erase information without violating its own laws. This tension between classical loss and quantum preservation is the heart of the information paradox. To drift deeper into this, imagine tossing a book into a black hole, a physical book with pages, ink, molecules, all arranged in a specific pattern. Classically, the pattern disappears beyond the horizon and remains trapped. Quantum mechanically, the arrangement of particles cannot be irretrievably lost. Something must give. Either quantum mechanics is incomplete, or classical general relativity breaks down near the horizon, or information is somehow encoded on the horizon's surface in a way we do not yet fully understand. Hawking's discovery of black hole radiation made this paradox even sharper. Quantum effects at the horizon cause the black hole to emit radiation, a faint thermal glow. This radiation allows the black hole to lose mass and eventually evaporate completely. If the black hole disappears, where does the information go? A thermal glow contains no detailed information. It is like steam rising from boiling water. The temperature tells you something, but not the shape of the pot or the recipe inside. If a black hole evaporates into pure thermal radiation, the information about what fell in seems lost. But quantum mechanics insists that information must always be preserved. This tension is subtle and quiet, yet it reaches into the deepest structure of the laws governing the universe. Some physicists propose that the information is carried out in slight deviations from perfect thermality, tiny imprints hidden in the radiation so subtle they might be impossible to detect. Others propose that the information remains encoded on the horizon surface itself, a kind of holographic archive that stores everything entering the black hole in a compressed, two-dimensional form. This holographic idea suggests that the surface of the horizon contains all the information about its interior, the way a hologram encodes a full three-dimensional image on a flat piece of film. Space inside may be emergent, a kind of deeper illusion arising from the information stored at the boundary. This concept is gentle and radical at the same time, that the universe might store information not in volumes but on surfaces. It is a way of reconciling classical silence with quantum preservation. Another idea is that the interior of a black hole is not disconnected from the outside as cleanly as classical physics suggests. Quantum entanglement may weave a deeper connection, binding inside and outside in subtle, non-local ways that allow information to flow without violating causality. Yet each idea, each attempt at a solution, comes with its own questions, its own gaps, its own puzzles. The horizon remains the quiet battleground where two frameworks of nature, one geometric, one quantum, offer different stories about how information must behave. To feel this tension more clearly, imagine something simple, a single photon falling inward. Classically, the photon crosses the horizon and is lost forever. Its path becomes a curve ending at the singular region. Quantum mechanically, the photon is a quantum state that cannot simply be erased. It must remain part of the universal wave function. Its information must go somewhere. But the horizon prevents signals from escaping. So how can this information return? This question is gentle and quiet in its phrasing, but profound in its implications. It is the kind of question physicists ask when the laws governing the universe seem to diverge at the edge of extreme conditions. The event horizon becomes not just a boundary in spacetime, but a boundary in theoretical understanding. This is why the information paradox has shaped so much modern physics, from string theory to holography to quantum gravity research to the study of entanglement entropy and the structure of spacetime itself. The paradox signals that our theories remain incomplete, not broken, just unfinished. They are two halves of a larger truth that we have not yet fully uncovered. And in this incomplete place, the horizon becomes a symbol of both mystery and opportunity, a boundary that invites deeper thought and deeper exploration, a line where physics remains correct, yet our explanations continue to evolve, a quiet threshold where certainty dissolves into curiosity. To drift even further into this, consider that some physicists propose that black holes do not destroy information, because evaporation is not purely thermal after all. Microscopic quantum correlations may encode the details of what the black hole consumed. These correlations would be unimaginably subtle, ripples of pattern woven into the radiation over billions of years. Others argue that the horizon itself is a thermodynamic membrane, a dynamic surface that absorbs, stores, and later re-emits information in altered form. Still others suggest that spacetime inside a black hole may not end in a singularity, but may continue into new regions where information is not destroyed but transformed. Each idea reflects a search for a deeper unity between quantum law and geometric curvature. The paradox persists because both frameworks feel true. Quantum mechanics works flawlessly in every tested regime. General relativity has never been wrong in its domain. And yet the two stories cannot both hold exactly as they are at the edge of a horizon. Something must give, something must expand, something must connect these truths into a larger, more complete picture. And in this space of inquiry, in this boundary between two great theories, black holes become laboratories for the deepest questions of physics. Not violent laboratories, not destructive, but quiet conceptual spaces where paradox becomes a guide. The horizon is not the place where physics ends. It is the place where our understanding is tested most deeply. A silent threshold where information seems to vanish yet must somehow remain. A place where the universe whispers one truth through geometry and another through quantum law, and invites us to listen for the harmony that connects them. The mystery of information near the horizon becomes even deeper when you consider how quantum entanglement threads its way through spacetime. Entanglement is not a force, not a signal, not a vibration. It is a relationship, a linkage between quantum states that persists even when the particles involved are separated by vast distances. When something falls into a black hole, its quantum state is entangled with the outside universe. Even a single photon carries entanglement with other photons, with fields, with the environment that helped create it. This means that the information associated with that particle is not stored solely in the particle itself. It is distributed, woven into a network of correlations. But when the particle crosses the horizon, the entanglement becomes stretched. Part of the quantum correlation remains outside, another part disappears inside. This creates tension in the structure of quantum theory. Because entanglement cannot simply vanish. If it breaks, it leaves behind contradictions, disturbances in the quantum fabric that physics does not permit. This is another facet of the information paradox. It is not just that information appears to be lost. It is that the relationships that define information must either persist across the horizon or be re-encoded in some new way. This leads to ideas that are surprisingly gentle, but profound. One idea suggests that the horizon is not empty, but filled with quantum microstates, tiny degrees of freedom that store information about everything that falls in. These degrees of freedom are invisible to the falling observer, yet real to the outside observer who sees the horizon as a thermal surface with entropy and temperature. In this view, the horizon behaves almost like a memory, a place where the details of the interior are written onto a two-dimensional sheet, compressed and encoded in ways we do not yet fully understand. This is the holographic idea, the notion that a region of space can be described by information living on its boundary. It is not metaphorical. It is a precise proposal that suggests the interior of a black hole may be a secondary description, emerging from the information encoded at the horizon. To drift deeper into this, imagine a hologram printed on a surface. The film itself is flat, yet when illuminated the image appears three-dimensional, with depth, structure, parallax, layers. Now imagine the event horizon acting as the film. The interior becomes the holographic image, not fake, not imaginary, but emergent. A different description built from information living on the boundary. In this perspective, the paradox softens. Information is not destroyed. It is stored in the horizon's degrees of freedom. And Hawking radiation, the glow emitted by quantum fluctuations, may carry that information outward over long timescales as the black hole evaporates. This idea retains unitarity, the quantum rule that information remains preserved. It respects the horizon's classical behavior. It preserves the experience of the falling observer who sees nothing unusual at all. A harmony begins to emerge, but harmony is not certainty. Not all physicists agree, and this is where the paradox deepens once more. Some propose that the horizon cannot remain smooth if information is encoded there. They argue that preserving unitarity requires the horizon to become energetic, filled with high-energy quantum excitations, a place where the falling observer would encounter a wall of intense radiation, a firewall, contradicting the smooth classical crossing predicted by relativity. This idea challenges the principle we have drifted with so far, that an infalling observer feels nothing at the horizon. In the firewall picture, the horizon becomes a place of violent quantum disruption, where entanglement must be broken in order to preserve the purity of Hawking radiation. The paradox shifts. Either information is lost, or relativity's smooth horizon fails, or entanglement must break in ways quantum mechanics seems to forbid. Yet firewalls come with their own contradictions. They clash with the idea that nothing special occurs locally. They conflict with the equivalence principle, a pillar of general relativity. They suggest that black holes are not calm after all, but fierce, and yet no evidence supports this. Our best understanding of physics still leans toward a smooth horizon. So the paradox persists, floating gently between these competing interpretations. Other approaches suggest that space and time themselves emerge from networks of entanglement, so the very distinction between inside and outside may dissolve at a deeper level. In these models, information is not in the black hole or on the horizon or outside in radiation. It is part of a unified structure that only appears separated because we view it through classical geometry. This view is harder to picture, but it carries a quiet elegance. It suggests that spacetime is not fundamental, that it arises from quantum relationships the way temperature arises from molecular motion. If so, the horizon might be a location where our classical notion of spacetime begins to fail, not because physics breaks down, but because we reach the limit of what classical spacetime can describe. Even within this conceptual space, the paradox remains an invitation, a doorway, a sign that the universe contains deeper layers we have not yet explored. To drift even further, imagine that Hawking radiation is not purely thermal after all. Subtle correlations might lace the radiation, carrying the fingerprint of every particle that ever fell in. These correlations would be faint, almost impossible to detect, but enough to preserve information as the black hole evaporates. In this picture, the black hole does not erase information. It scrambles it. It distills it. It encodes it in a chaotic but reversible pattern woven into the outgoing radiation. The paradox softens again. Information is not lost, but hidden. Hidden too deeply for us to recover with any current instrument. Hidden in the quantum fabric in a way that only a complete theory of quantum gravity could fully describe. Another idea is that the interior of the black hole is not disconnected from the exterior in the way classical geometry suggests. Some physicists propose that wormhole-like structures, Einstein-Rosen bridges, could provide an entangled connection between interior and exterior states, allowing information to remain consistent without violating causality. Not literal wormholes one could travel through, but quantum geometries that maintain the coherence of the global state. This is where the paradox becomes soft, almost dreamlike. We are no longer dealing with physical tunnels, but with mathematical relationships between distant regions of space-time. Information may not need to escape. It may never be lost in the first place. It may remain part of a single quantum whole. Through all of this, the horizon remains the quiet center, the surface where the tension between theories is most pronounced, a place where gravity and quantum mechanics meet and disagree, not violently but thoughtfully, like two scholars offering two interpretations of the same manuscript. Neither interpretation is complete. Both hold fragments of truth. The horizon is where those fragments touch. And as you drift with this idea, you begin to feel the calmness behind the paradox. It is not a sign of contradiction, but a sign of incompleteness. A whisper that our current theories are approximations of something deeper. There is no urgency here, no rush. The universe keeps its secrets patiently. Black holes evolve slowly. Information escapes or transforms over timescales longer than the age of stars. Physics offers time to understand, time to think, time to refine our models until the paradox becomes a window into the next chapter of fundamental theory. This is why many physicists view the information paradox not as a crisis, but as a clue, a signpost, a guiding question pointing us toward quantum gravity, the unification of quantum mechanics and spacetime curvature. The horizon becomes the boundary where this unification is most needed, a place where two descriptions overlap and disagree in just the right way to illuminate what is missing. And in this quiet, conceptual space, you begin to sense that the universe is encouraging us to listen more closely, to look more deeply, to embrace the unknown as part of the beauty of understanding. In the calm darkness surrounding a black hole, the shape of the event horizon seems simple at first glance, a sphere, smooth and symmetrical, defined only by mass. But this simplicity dissolves the moment the black hole begins to spin. Rotation changes everything. It changes the geometry, it changes the structure of space-time, and it changes the horizon itself. A rotating black hole pulls on space-time, twisting it gently but relentlessly, as if stirring the fabric of the universe with a silent motion. This twisting is not a metaphor. It is a measurable feature called frame dragging. Mass curves space, but spinning mass drags space along with it. And so the horizon of a rotating black hole is no longer a perfect sphere. It flattens slightly at the poles, bulges at the equator, and becomes the boundary of a space-time that is no longer static but dynamic, swirling, alive with rotation. To drift deeper into this idea, imagine that space-time near the black hole is like a slow-moving whirlpool, not a violent one, but a vast cosmic eddy in which everything is gently compelled to move with the rotation. The closer you drift, the stronger the pull becomes, until there comes a region where movement is no longer optional. This region is called the ergosphere. It sits outside the event horizon itself, a swollen, distorted shell where space-time is dragged so forcefully that even standing still is impossible. Everything, light, matter, radiation, must rotate in the direction of the black hole's spin. Inside the ergosphere, the nature of motion changes. You can move forward, you can move inward, but you cannot resist the frame dragging. You cannot remain stationary with respect to the distant universe. In this region, energy can be extracted from the black hole's rotation. This is a consequence of geometry, not machinery. Particles entering the ergosphere can split into two paths, one falling inward with negative energy relative to infinity, and the other escaping outward with greater energy than it had when it entered. This process does not violate physics. It is simply the geometry of rotating space-time expressing itself. The black hole loses a tiny amount of rotational energy, and the escaping particle carries it away. This means that rotation is not permanent. Over unimaginable timescales, a spinning black hole can gradually lose its spin through interactions with the universe around it. And as the spin changes, the horizon changes too. The radius of the event horizon shrinks in the direction of the poles and expands around the equator the faster the black hole spins. At the maximum possible rotation rate, a theoretical limit called an extreme Kerr solution, the horizon becomes as flattened as geometry allows, hovering at the edge of instability. The shape of space-time here is more exotic than the simple classical image suggests. Closed orbits twist, light paths bend in spirals, and the flow of time itself depends on the direction you move. Clock rates differ not only by distance but by orientation relative to the spin. This is a region where intuition begins to slip, not because the physics is unclear, but because space-time behaves in ways the human mind has never experienced. Up and down lose meaning. Directions that are normally independent begin to influence each other. Motion that seems free becomes constrained by an invisible geometry. Even the concept of an escape path changes with spin. Light cones, those geometric structures that define all possible future trajectories, tilt dramatically near a rotating horizon. They lean in the direction of rotation, making some paths easier to follow and others impossible to achieve. Inside the ergosphere, the light cones tilt so far that all allowed directions carry you forward with the spin. Only outside this region can a photon choose whether to rotate with the black hole or resist. This is why the ergosphere is not merely a curiosity. It is a genuine physical region where the rules of motion are altered in a way that has no equivalent around a non-rotating black hole. Deeper still, the event horizon itself becomes dynamic as the black hole interacts with its environment. If mass falls in unevenly, in clumps or streams, the horizon can momentarily ripple, stretch, and deform before settling back into its equilibrium shape. These distortions are not like waves on water. They are changes in the geometry of spacetime itself. When two black holes merge, their horizons distort violently before becoming smooth again. This settling process emits gravitational waves, faint ripples in spacetime that carry information about the final horizon's shape and rotation. The horizon is not a hard boundary. It is flexible, responsive, sensitive to the flow of mass and energy around it. Its position depends on the mass and spin at each moment in time. Even the notion of inside and outside becomes less definite when the black hole is rotating. For non-spinning black holes, the horizon is clear and symmetric, but for spinning ones, the static limit, the boundary of the ergosphere, sits outside the horizon, creating two distinct surfaces that shape the structure of spacetime differently. The static limit marks the place where no object can remain motionless relative to the distant universe. The event horizon marks the place where escape is impossible. Between them, spacetime becomes a region where motion is compelled but not yet doomed. This dual surface structure is one of the most unique signatures of rotating black holes, and it highlights something subtle and profound. The horizon is not singular. It is part of a family of boundaries that depend on how the black hole moves and how spacetime reacts to that motion. Rotation also affects the interior geometry. The nature of the central singularity shifts profoundly. In a non-spinning black hole, the singularity is a point, a location where curvature becomes infinite in all directions. But in a rotating black hole, the singularity becomes a ring, a loop, a thin circular structure hidden deep within the warped spacetime. Its presence changes the interior paths that objects could take if they fall all the way inward. The mathematics suggests that trajectories might pass through the ring into other regions of spacetime, though these solutions are almost certainly unstable in reality. Quantum effects, collapse dynamics, and the breakdown of classical geometry likely prevent such pathways from existing physically. But even the possibility shows how rotation alters every aspect of the horizon's structure, from the outermost surface to the deepest interior. It suggests that the horizon is not a static concept. It is a living boundary, responsive to angular momentum, mass, and the dynamic interactions that take place over astronomical timescales. When a black hole accretes matter from a star, a gas cloud, or an orbiting disk, the direction of that matter's angular momentum changes the spin. If the infalling matter orbits in the same direction as the black hole's rotation, the spin increases. If it orbits in the opposite direction, the spin decreases. This subtle exchange is fully encoded in the geometry. The horizon shifts with each new contribution, changing shape to reflect the evolving angular momentum. Even the maximum spin is limited by physical constraints. A black hole cannot spin infinitely fast. If it tries to approach that extreme, its own geometry prevents additional angular momentum from being added. This is not a mechanical resistance. It is a geometric one, written into the equations of general relativity. The horizon, therefore, is not merely a boundary. It is an evolving, curved, rotating structure defined by the balance between gravity, angular momentum, and the flow of spacetime itself. To rest with this idea is to recognize that black holes are not simple objects. They are dynamic, responsive, geometric entities that shape their surroundings in ways that defy ordinary experience. The notion that a horizon can stretch, twist, flatten, or shift with rotation or infalling matter suggests that even the most extreme environment is not static. It evolves with the universe, subtly and slowly, over long spans of cosmic time. As you drift through this understanding, you sense how quiet the underlying mathematics truly is. Nothing in these descriptions is chaotic. Nothing is rushed. The evolution of a rotating horizon is composed of gentle changes in curvature and geometry, the cosmos adjusting itself with calm precision. And through this quiet evolution, the horizon reveals its true nature. It is not a line, not a fixed membrane, not a single surface. It is a dynamic boundary defined by the deep structure of spacetime itself. As you drift deeper into the nature of rotating black holes, you begin to realize that the horizon is not just a boundary that marks where escape becomes impossible. It is a surface shaped entirely by the balance between rotation and gravity, between motion and curvature, between the inward pull of mass and the sideways pull of angular momentum. This balance is delicate, not fragile, but precise, as if spacetime itself keeps careful track of how much twist and how much gravity are woven into the structure. Rotation forces the geometry to adapt, and one of the clearest signs of this adaptation is the way the horizons, the event horizon and the static limit, separate from one another. To understand this separation, imagine drifting toward a rotating black hole from far away. From a distance, the black hole looks almost the same as a non-spinning one. Mass is mass, and curvature follows the familiar pattern. But as you drift closer, you begin to sense motion in the geometry itself. It is not visible motion, not a swirling in the air, but a gentle, mathematical rotation etched into the shape of spacetime. And then you reach the static limit. This is the outermost boundary of the ergosphere, the region where frame dragging is so strong that you can no longer remain still with respect to distant stars. Even if you fire your engines to counter the rotation, you will still be carried along, slowly at first, and then more strongly as you drift inward. The static limit is not the event horizon. You can still escape from here. You can still turn around and fly back to safety. But you cannot avoid moving sideways with the spin of the black hole. This is the first sign that the horizon is not a simple surface. It is part of a layered structure, a set of nested boundaries defined entirely by geometry and the behavior of light cones. As you drift closer still, the tilt of the light cones becomes more dramatic. These cones represent all possible future directions that you can move in, and they lean ever more sharply toward the direction of rotation. The closer you come, the more your possible future is forced to align with the black hole's spin. At the event horizon, the cones tip so far inward that escape becomes impossible. Every possible future leads you deeper into the space-time well. This tilt is not sudden. It is gradual, smooth, continuous, a quiet shift in the fundamental structure of how motion behaves. The horizon, in this sense, is not a line in space but a tipping point in geometry, a place where the possible futures narrow down to a single inward path. The fact that rotation changes this tipping point reveals something profound. Mass alone does not determine the horizon. Spin contributes just as deeply. The faster the rotation, the more the horizon stretches and flattens, and the more the tipping angle changes from point to point. This leads to a subtle truth. There is no single radius for a rotating horizon. The distance from the center depends on the direction. Closer at the poles, farther at the equator, the horizon becomes a shape that defies perfect symmetry, quietly adjusted to the flow of angular momentum. And as the black hole spins faster, another layer of structure emerges. The region between the static limit and the event horizon grows thicker, wider, more pronounced. This region is the ergosphere, and it is one of the most remarkable features in all of physics. Inside it, motion is not optional. Even photons, the most independent travelers in the universe, are forced to rotate. Their paths, normally free and unconstrained, become tied to the geometry of the rotating spacetime. This enforced motion is not a force acting on them. It is simply the shape of the light cones, tilted so strongly that no future path exists that does not rotate. Light behaves this way because spacetime itself behaves this way. The ergosphere shows clearly that rotation affects geometry in a way mass alone cannot. It is a physical region where energy extraction is possible, where trajectories can split, and where the black hole can gradually lose angular momentum through natural processes. This gradual loss softens the geometry. The ergosphere becomes thinner, the bulge of the horizon less pronounced, the tilt of the cones less extreme. Over cosmic timescales, a spinning black hole can become more spherical as it radiates energy away or absorbs matter moving in the opposite direction. The horizon reflects all of this. It contracts or expands depending on the balance between mass and spin. The geometry changes, not abruptly but smoothly, gently, as if space-time adjusts itself with infinite patience. And then there is the most dramatic transformation of all, the one that happens during black hole mergers. When two black holes spiral together, their horizons begin to distort long before they touch. Each horizon feels the curvature of the other. They stretch, compress, and warp into elongated shapes that resemble tidal distortions in spacetime. Just before they merge, the horizons form a kind of geometric bridge, a funnel-like structure that connects the two surfaces in a brief moment of extreme curvature. When they finally collide, the combined horizon shakes violently. It quivers, oscillates, and emits gravitational waves as it settles down. These waves carry away information about the final black hole's mass and spin, allowing the horizon to relax into its new, stable shape. This settling process reveals something subtle. The horizon behaves like a physical membrane, not a rigid one, but a flexible, dynamic surface that can ring like a drum of space-time. And the tones of that ringing, the frequencies and damping times, are predicted precisely by general relativity. The fact that we have detected these gravitational tones tells us that the horizon is not a fixed barrier. It is a surface that responds to disturbances in geometry. It vibrates, releases energy, and settles into equilibrium with a calmness that mirrors the universe itself. The vibration of the horizon is not a mechanical motion. It is the evolution of curvature. The surface smooths itself as the space-time equation removes all unnecessary complexity. The final state is simple and elegant, a rotating black hole described by only mass and spin. This is one of the most astonishing facts in all of physics. Despite the complexity of the matter that formed it, despite the chaos of the merger that created it, the final black hole remembers almost nothing. All details of the matter that fell into it are erased, leaving only two numbers to describe the exterior geometry: mass and angular momentum. Everything else is lost inside, and yet the horizon remains dynamic. It continues to adjust whenever new matter falls in, or when the black hole emits energy through slow processes like Hawking radiation. This adjustment is not visible from the outside in any direct way, but it changes the position and shape of the horizon in a manner consistent with the conservation of energy and the structure of space-time. Even on the smallest scales we can imagine, the horizon cannot be perfectly static. Quantum fluctuations ripple across it, tiny deviations from the classical shape, suggesting that the horizon, when viewed up close, is an active participant in the quantum structure of spacetime. These fluctuations are subtle. They are not waves, not vibrations, not movement in the familiar sense. They are statistical variations in the geometry itself, a whisper of quantum gravity that classical theory cannot fully describe. This reminds us that the horizon is not a simple boundary between inside and outside. It is a region where the known laws of physics reach their limit, where classical geometry meets quantum uncertainty. Everything about the horizon reflects this dual nature. Its shape is classical, but its fluctuations are quantum. Its position is defined by the equations, but its microstructure is governed by deeper rules that we do not yet understand. This interplay makes the horizon one of the most mysterious structures in the universe. It looks simple, but contains layers of complexity woven into its geometry. It behaves predictably, but hints at phenomena beyond our current theories. It is shaped by gravity, but may encode information in ways that no classical surface ever could. And through all of this, the horizon evolves. It responds to rotation, to mergers, to the flow of matter and energy, and perhaps even to quantum processes that we have only begun to imagine. It is not a line, not a shell, not a static, immutable boundary. It is a living structure written into the fabric of space-time. It is shaped by mass, bent by spin, softened by radiation, distorted by mergers, and stirred gently by the quiet touch of quantum fluctuations. To rest with this understanding is to appreciate the full subtlety of the event horizon. It is geometry made fluid, curvature made dynamic, a boundary that shifts and swirls and breathes with the universe around it. It is not a line. It is a story written in space-time. There is a moment, as you drift toward the event horizon in thought, where the physics begins to soften in a way that feels different from everything before. Not because the equations fail, but because the questions themselves begin to exceed what our theories are built to answer. The event horizon becomes not just a boundary in space-time, but a boundary in understanding. A threshold where our best descriptions reach their limits. A place where the mathematics continues smoothly, yet the interpretation becomes uncertain. This is where classical physics and quantum theory begin to disagree, not violently, but quietly, as if each is whispering a slightly different story about what lies at the edge of a black hole. The horizon becomes a meeting point between these stories. General relativity tells us that the horizon is a smooth, regular surface. Crossing it is uneventful. Nothing special happens locally. Spacetime continues to curve, but the journey inward feels no different from drifting through any other region of strong gravitational field. Quantum theory, though, looks at the horizon and sees a thermodynamic structure, a surface with entropy, with temperature, with microscopic degrees of freedom that are invisible in classical geometry. It does not contradict relativity, but it adds a layer of complexity that relativity does not describe. And so the horizon becomes two things at once: a perfectly ordinary region of space-time and a place where information behaves in ways that seem paradoxical. This duality marks the beginning of the boundary of understanding. One part of the mystery is that the horizon is the limit of what can be predicted. If an event occurs behind the horizon, no signal can propagate outward to reveal it. The information about that event is sealed away by the structure of space-time. Classically, this is simply how gravity works, but quantum mechanics insists that information cannot disappear. Unitary evolution demands that the full state of a system must remain encoded somewhere within the universe. And so the horizon sits quietly between these principles, general relativity allowing information to vanish, quantum theory forbidding it. This tension is not a failure of physics. It is a clue that deeper principles have not yet been discovered. The horizon, then, is not just a boundary in space. It is a boundary in theory, a place where our current understanding reaches its edge and must eventually give way to something new. As you drift through this idea, you feel how calm it is. The horizon does not demand a resolution tonight. It simply exists, quietly marking a point where the known laws of nature meet their own incompleteness. Even Einstein's equations hint at this incompleteness. They describe the curvature of space-time beautifully, but they say nothing about the quantum structure of that curvature. Nothing about how space-time behaves on the smallest possible scales. Nothing about how gravity interacts with the quantum fields that define the rest of physics. At the horizon, these missing layers become impossible to ignore. Some theories propose that space-time near the horizon is woven from microscopic elements, tiny quanta of area that carry information and collectively produce the thermodynamic properties we attribute to black holes. Others suggest that the horizon is not fundamental at all, that it is an emergent phenomenon, a large-scale behavior arising from deeper patterns that we cannot yet perceive. In these views, the horizon is like the surface of water. You can describe the surface with equations of fluid motion, but the surface itself is not fundamental. It is a collective effect of countless molecules moving in coordinated ways. The event horizon may be similar, a macroscopic feature emerging from microscopic constituents that do not resemble space-time in the classical sense. And if this is true, then the horizon is not where physics breaks down, but where our picture of physics shifts from one level of description to another. This possibility has driven an entire branch of research into quantum gravity, an attempt to combine the smooth geometry of Einstein with the discrete, probabilistic framework of the quantum world. At the edge of the horizon, this unification becomes essential. Here, the gravitational field is strong enough that space-time curvature can no longer be treated as a simple background. Quantum effects matter. Fluctuations matter. The vacuum itself has energy and structure that classical theory cannot describe. And yet, for all the mystery, the horizon remains quiet. It does not reveal what lies beyond our current theories. It simply holds its place, like a silent teacher who allows you to sit in the presence of a question without rushing to answer it. Another layer of the boundary of understanding comes from the predictions of quantum field theory. Near the horizon, the vacuum is unstable. Particle-antiparticle pairs form and dissolve in the intense curvature. One of these particles can fall inward, while the other escapes as radiation. This is Hawking radiation. It is gentle. It is slow. And it suggests that black holes evaporate over unimaginably long timescales. But evaporation introduces a tension. If a black hole disappears, where does the information go? Does it seep out encoded in the radiation? Does it remain stored in correlations that we do not yet know how to decode? Or does the horizon hide a new mechanism entirely? Each possibility challenges something fundamental, either unitarity or locality, or the geometric interpretation of spacetime. And yet the horizon endures. It does not choose a side in the theoretical disagreements. It simply exists at the intersection of these competing principles. The more deeply we study the horizon, the more it reveals the limits of classical physics. The curvature becomes so extreme that the very concept of distance loses meaning at small scales. The geometry becomes sensitive to quantum fluctuations that Einstein's equations cannot accommodate. Some theorists believe that the horizon may be a thermodynamic interface, a surface where entropy, temperature, information, and geometry interact in ways that blur the distinction between matter and spacetime. Others propose that the horizon is holographic, a projection of information stored not in the volume within, but on the surface itself. If this is true, then the interior of the black hole may be a kind of illusion, a mathematical construction emerging from the information encoded at the boundary. This idea does not diminish the interior. It simply reframes it as part of a deeper principle, that information in the universe may be stored on surfaces rather than in volumes. If this principle is correct, then the horizon is not merely the edge of a black hole. It is a fundamental surface where the architecture of reality is expressed. A final layer of mystery comes from the simple fact that we cannot test these ideas directly. We cannot send instruments across the horizon and retrieve their data. We cannot probe the interior geometry with signals that return to us. And so the horizon becomes a natural boundary for knowledge itself. Not because the truth is hidden, but because the structure of spacetime prevents us from asking certain questions in the usual way. To sit with this is to accept that not all mysteries exist to be solved immediately. Some exist to invite contemplation. Some exist to show us the edge of our current frameworks. Some exist to remind us that science is not finished, that discovery is ongoing, that deeper principles wait quietly in the dark beyond the reach of present theories. The horizon does not hide answers. It highlights the contours of our own ignorance with gentle precision. It shows us where our understanding ends and where the next great ideas must someday arise. And through all of this, the horizon remains peaceful, silent, serene. It is the boundary of understanding, not because it is violent, not because it resists explanation, but because it invites us to imagine what lies beyond the reach of current physics. It encourages a calm acceptance of the unknown, a quiet trust that mystery is not a flaw in the universe, but a feature that keeps curiosity alive. Here, near the event horizon, you can rest in the presence of questions that have no answers yet. You can drift through the realization that knowledge has edges, and that those edges are beautiful. You can feel the calm of a universe that does not rush to reveal all of its secrets. It simply offers them slowly, patiently, as our understanding grows. As you drift deeper into this final region of thought, you begin to sense that the event horizon is more than a physical boundary or a conceptual limit. It is a place where the nature of explanation itself starts to unravel, where the familiar language of physics grows quiet and new patterns wait beneath the surface of our understanding. The mystery does not come from chaos or contradiction. It comes from subtlety, from the gentle realization that the universe may be built from layers of structure that do not reveal themselves all at once. The horizon stands at the threshold of those hidden layers. One of the deepest questions that emerges here is whether space-time is fundamental. General relativity treats it as a smooth, continuous fabric, a geometric entity that curves, flexes, and determines how matter moves. But quantum theory asks a different question. Could this fabric be woven from something smaller, something more discrete, something that behaves like a thermodynamic medium at the smallest scales? If so, then the horizon becomes a kind of surface where the deeper constituents of spacetime express themselves. Entropy, temperature, and information may not be side effects, but primary clues to the microscopic architecture hidden beneath the geometry. This shifts the role of the horizon from a passive boundary to an active structure. Not active in the sense of motion, but active in the sense that it carries degrees of freedom, tiny variables that encode information about everything that has ever fallen inward. These degrees of freedom are not visible in relativity. They are not part of the smooth curvature. They belong to something deeper. Something that behaves like a quantum system with an enormous number of possible internal configurations. If this picture is correct, then the horizon is not simply the edge of a black hole. It is a thermodynamic boundary where the microscopic elements of spacetime arrange themselves into patterns that our equations translate into geometry. This does not reduce the horizon to something familiar. It elevates it into a new category of structure, a surface where gravity, quantum theory, and thermodynamics merge into a single expression. The idea is gentle yet profound. It suggests that the horizon may not be the end of understanding, but the beginning of a new way of thinking about physics. Another possibility goes even further. Some proposals in quantum gravity suggest that the event horizon may not be fundamental at all, that it might arise only from the way observers organize information about the region around a black hole. In these viewpoints, the horizon resembles a mirage, not in the sense of being unreal, but in the sense that its existence depends on perspective and description. It is like the boundary between past and future in the flow of time, a real feature in experience, but not a physical surface made of atoms or fields. In these models, the horizon appears because observers outside the black hole have limited access to information. The geometry we assign to it is a reflection of that limitation. Whether this picture is correct remains unknown, but it highlights a deep possibility. The horizon may not be a fundamental object, but an emergent one. This does not diminish the horizon, it enriches it. It says that the boundary where physics breaks down is not a flaw, but a clue that the universe contains layers we have not yet understood. Another thread of mystery comes from considering the singularity, the central region where curvature becomes infinite in the classical description. General relativity predicts it, but quantum mechanics cannot accept it. Infinity is a sign that a theory is being pushed beyond its intended domain. Some theories suggest that the singularity dissolves into a dense quantum region where classical geometry stops being meaningful. Others propose that spacetime may bounce, that the interior may connect to other regions, or that quantum effects smear the singularity into a finite structure with no divergence. The horizon sits just outside this region. It acts as a quiet curtain around the unknown interior. It prevents us from witnessing what really happens when gravity becomes strong enough to overcome every other force. This curtain is not hostile. It is not hiding anything malicious. It simply reflects the structure of spacetime, a natural limit on how information can propagate. The mystery lies not in the curtain, but in what it surrounds. The interior may be smooth or chaotic or structured or emergent, or something entirely beyond our current ways of describing reality. The horizon marks the place where our predictions no longer reach inward. It separates the region where physics is fully predictive from the region where physics becomes silent. This silence is not a failure. It is a signal that new principles are waiting to be discovered. This leads to another quiet but profound idea, that the horizon might be a thermodynamic system. It possesses entropy proportional to its surface area. It emits radiation with a temperature inversely proportional to its mass. It behaves, in every measurable way, like a system with internal states and statistical behavior. If the horizon has entropy, then it must have microstates. And if it has microstates, then the geometry we see is only the macroscopic shadow of something far more detailed. These microstates are not part of classical spacetime. They belong to a deeper theory that has not yet been fully understood. Some hints come from string theory, others from loop quantum gravity, others from holographic dualities that describe black holes in terms of lower dimensional systems. Each approach offers a different insight. Each approach captures a piece of the puzzle. But none of them provides the complete picture. The horizon remains a boundary of understanding because the full structure of spacetime's microphysics has not yet been revealed. Even the simple question, what is the horizon made of, has no definitive answer. It may be composed of discrete quanta of area, or of entanglement across regions, or of topological constructions that have no classical analog, or of something so unfamiliar that we do not yet have the language to describe it. The horizon invites us to stop insisting on immediate clarity. It asks us to accept, for a moment, that not knowing is a natural state at the edge of discovery. There is a quiet comfort in this. The universe does not rush to reveal its deepest mechanisms. It offers them slowly, on cosmic timescales, as our theories evolve. Another deep question emerges when we think about the fate of information in a universe with horizons. If a black hole evaporates through Hawking radiation, what becomes of the information that fell inside? Does it come out encoded in subtle correlations in the outgoing radiation? Does it remain stored in a quantum remnant? Is it reconstructed by holographic duality? Or does the horizon undergo a transformation in its final moments that releases the information in a way we cannot yet imagine? Each possibility reveals a tension between the principles of quantum mechanics and the predictions of general relativity. This tension does not mean that one theory is wrong. It means both are incomplete. The horizon sits at the intersection of these incomplete pictures. It is the place where the next generation of physics will eventually take shape. To drift through this realization is to see the horizon not as a barrier, but as a guide. It points to the questions we must ask next. It shows us where the future of theoretical physics must turn its attention. It marks the boundary between what we know and what we are still capable of discovering. And through all of this, the horizon remains peaceful. It is not a place of violence. It is not a place of conflict. It is a place of transition, a region where the known meets the unknown with quiet dignity. It is a reminder that the universe is allowed to be mysterious, that complexity does not diminish beauty, that uncertainty is not a threat but an invitation. The horizon teaches that understanding is always provisional, that every answer opens new questions, that knowledge itself has edges that move outward as our theories grow. As you drift with this idea, you feel the calm that comes from accepting that not everything must be resolved tonight. You can rest in the presence of unsolved problems. You can breathe in the quiet of unanswered questions. You can sleep knowing that the universe continues to unfold its secrets slowly, gently, in its own time. The horizon waits patiently for new physics to arrive. It is not in a hurry, and neither are you. As you drift toward the end of this quiet journey, you feel the vastness around you soften, as if the universe itself is exhaling. The event horizon, which once felt distant and abstract, now feels familiar, like a place you've visited in thought long enough for its strangeness to become gentle. It is not a wall, not an edge, not a warning. It is simply a boundary between what physics can describe and what it has not yet learned to express. You have walked alongside the mathematics that shape it, the geometry that bends light, the slowing of time, the hidden layers of information, the shifting surfaces of rotating space, and the mysteries that still wait for future theories to reveal them. And now, as the journey eases to a close, you return from that boundary with a calm sense that the unknown is not something to fear. It is something to breathe with, something to let settle quietly in the background of your thoughts, like a horizon at dusk, blurring into the sky. As you move gently away from the region around a black hole, you realize that nothing here was meant to be solved tonight. Not the paradoxes, not the conflicting perspectives, not the complex structures of spacetime's hidden depths. All of it was meant to drift through your mind like soft currents, light, slow, unhurried. Understanding was never required, only presence. The event horizon remains in the distance, a curved region of spacetime defined not by sharp edges but by the quiet surrender of light. A place where signals stretch thinner and thinner until they fade into long wavelengths that drift into silence. From far away, you sense again the strange duality, how a distant observer never sees anything cross the boundary, yet a falling traveler slips through without resistance. Two truths, each correct in their own frame. This duality is not confusion. It is a reminder that the universe can hold multiple perspectives without contradiction. As you drift farther back, you feel the theoretical tension that lives at the heart of black hole physics, the push and pull between relativity and quantum mechanics, between smooth geometry and discrete information, between horizons and radiation, between entanglement and evaporation. But the tension does not disturb you. It simply settles around you like a soft fog, reminding you that the deepest questions do not always need answers to offer comfort. Sometimes presence is enough. The black hole remains behind you, quiet, motionless, yet deeply alive with invisible processes too subtle for human senses to perceive. Its horizon glows faintly in your thoughts, not with light but with significance. It is a reminder that limitations can be beautiful, that the edges of knowledge are part of what gives science its depth and shape. Even the entropy of the horizon feels gentle now, a measure of the hidden information woven into its surface. You no longer imagine it as something violent or chaotic. Instead, it feels like the texture of an unfinished story, a quiet archive of everything that has ever fallen inward, waiting for the universe to reveal how the final pages are written. This sense of incompleteness is not unsettling. It is peaceful, because it shows that the cosmos still has room to grow, room to reveal, room to surprise. You drift still farther away, and the gravitational curvature begins to flatten, the extreme warping softening into the gentle geometry of ordinary space. Time, which near the horizon stretched and warped into strange asymmetries, begins to flow again in familiar patterns. Seconds become steady, distances become calm. The fabric of spacetime returns to a place where human intuition feels at home. And yet you carry with you the memory of how different time can be when gravity intensifies. You remember the way a falling traveler experiences nothing unusual while the outside observer watches events slow towards stillness. These paradoxes do not unsettle you anymore. They rest softly in your mind as examples of how flexible the universe truly is. As you drift, your thoughts wander to the far future, a distant age when physics may finally discover how spacetime emerges from deeper principles, when quantum gravity is no longer a dream but a functional description of the universe's smallest scales, when horizons are understood not as mysteries, but as natural expressions of spacetime's subtle machinery. That future will come in its own time. It does not need to arrive tonight. It does not need to arrive within any lifetime. The universe moves slowly, patiently, on scales far beyond human urgency, and you are allowed to rest within that patience. You drift even farther, light years unfolding like wide fields of darkness around you. Stars scattered as faint points of light, cosmic dust like whispering clouds shimmering in silence. The black hole now is a distant dot, its horizon invisible, its influence softened into the background of galactic structure. What remains is not its presence, but the calm you carried away from it. A calm shaped by the realization that the unknown can be gentle, that unanswered questions can be serene, that mystery can nourish the imagination without demanding resolution. Your breathing slows, your thoughts grow lighter. The vastness around you feels like an open cradle, soft, quiet, undemanding. The universe is not asking you to solve anything tonight. It is offering you a peaceful place to rest within its endless expanse. You feel the weight of curiosity soften, not vanish, but relax, stretching out like a cat settling into a warm patch of sunlight. You can return to the event horizon whenever you wish, in waking thought, in imagination, in dreams. It will be there as a quiet landmark in the landscape of physics, a reminder that boundaries are only beginnings in disguise. For now, you drift even farther until the black hole fades completely from view. All that remains is the quiet hum of the cosmos, the gentle vibration of space-time, the still, steady presence of a universe that does not demand understanding, only wonder. And in this moment, you allow yourself to rest inside that wonder, to breathe within it, to relax into it as the last thoughts of the day grow soft and spacious and beautifully calm. The universe holds you in its quiet. Let yourself drift.